looks like we have a good number, so I'll go ahead and get started. So I want to welcome Tessa Fisher, who is a PhD candidate at Arizona State University, studying astrobiology and planetary habitability with Dr. Sarah Walker. And beyond her research, Tessa is also a science fiction and fantasy author. So Tessa, I'll take it over to you.
Thank you for that lovely introduction. So can everybody see my slides?
Looks great.
Okay, cool. So yeah, today I'm going to be talking about what has pretty much been my life's work for about the last 2 years. We recently had our first paper out on the topic, I guess, end of March. But basically, it's a sort of a new methodological approach to understanding exoplanet atmospheres with a particular focus on eventually, hopefully, developing better ways of detecting biospheres. So, as I'm sure most of you know, within the next 10 to 20 years, we, at least in theory, will have reached the capability where we will be able to at least get some sense of the atmospheric composition of Earth-like exoplanets, which is great. However, as an astrobiologist, I think the major problem we're running into is with that information. Okay, how do we go from having a one-dimensional spectra to being able to confidently say that there's life on the planet? So that's just to give you a background. That's kind of what motivated this project, because traditionally with astrobiology, there's been a sense that, oh, well, we just look for oxygen, since most of the oxygen on Earth comes from plants or from methane. That mostly comes from bacteria. Turns out, though, as we've kind of realized the true diversity of worlds that are out there, and also gotten better at modeling the sort of formation and evolution of planetary atmospheres, that there's a lot of ways you can get an oxygen-rich atmosphere that have absolutely nothing at all to do with biology. So there's a real looming problem or threat, I guess, of false positives. And the other problem with this approach of just, we look for the biologically relevant gases on Earth, is that we're assuming that whatever biospheres we find are going to be very similar to our own, using carbon as their primary backbone, liquid water as a solvent, oxygenic photosynthesis. And that may not be the case. I mean, oxygenic photosynthesis only really came to dominate the Earth's biosphere and, consequently its atmosphere about 3/4 of the way through its history so far. So, for most of the time span that the Earth has been around, you wouldn't be able to use oxygen to detect the presence of life there. And, for some of these different biochemistries and, formulations of biospheres, we may not necessarily know what the most biologically relevant trace gas in the atmosphere is going to be. So that's another potential problem with sort of the smoking gun technique of just looking for one or two biosignature gases. So instead, the approach that we're taking in the lab I'm in is looking at, rather, instead of just looking for one or two specific biologically relevant gases, we are trying to understand the behavior and statistical pattern of interactions between gases in an atmosphere and see if that can tell us the information that we're looking for. And the way we do this is by representing them as networks, where every species present in the atmosphere is represented as a point, and then they are connected to each other based off of what reactions they co-participate in. And I'll have some examples of this in a bit. And when I talk about networks and measuring them, what are the sort of things I'm talking about? One of them is degree, which in plain English is the number of connections to a given point or node in network jargon in a network. And if you're looking at a whole network, you can take the mean degree, which is on average the degree of any given node in a network. So it's taking, well, exactly what it sounds like. Another pretty self-explanatory measurement we've been looking at is the shortest path length, which is, again, as the name suggests, the shortest distance between any two nodes in a network. And again, looking over the whole network, you can look at the average shortest path length, which again, on average, is the shortest distance between any two given nodes in a network. So these average measurements are really good for getting a sense of what the shape and topology of the network is as a whole. There we go. Now, another thing you can do with networks is incorporate information you know about the relationships between this different and various subcomponents of the network into the connections or edges, again, another network jargon, between them. And you can represent any quantifiable measurement or metric between any 2 points, as long as you can quantify something about the nature of their interaction. And to give you an example of how this might come in handy, let's take this really simple network. So if this were an unweighted network that is each connection or edge was given the exact same value, and you want to know what the shortest distance between point A and point C is, it'd be really simple. It would be from going from point A to point B to point C, because there's only one intervening point between them. However, let's say that the weights we've assigned to this network actually represent, say, physical distance. And in which case, the shortest distance isn't going from A to B to C. It's going from A to B to D to C, because the weighted distance between A and C, or from A to B to C, is only 5, whereas the weighted distance between A to B to C is 6. So again, this is something else that can make networks really useful for characterizing sort of the interactions between components of the system, is that you can incorporate this information in a very intuitive way. So again, we can do this with chemistry. You can set up chemical reaction networks. Again, like I said, you can take the various species that are present in the atmosphere and then connect them based off of what reactions they could participate in. This is a really simple example that you see up here from Solé and Montanou's paper 2004. And the primary reason we're looking at atmospheric chemical reaction network topology in particular, it has to do with this paper from 2004 in particular, because when Solé and Montanou did this sort of analysis for all the major planetary atmospheres in our solar system, most of them looked like this. I believe this one is for Mars in particular. However, when they looked at the network for Earth, it looked like this. Obviously, very different structure from the other planets in our solar system. It's modular in that it's kind of divided up into easily discernible subcomponents. It's hierarchical in that the subcomponents feed into each other, from one level to another. And it has a lot of really interesting topological properties that you don't see in other atmospheric chemical reaction networks. And naturally, something that we're trying to figure out is, well, is this unusual topological structure the result of the presence of a thriving biosphere that is closely intermeshed with the planet's atmosphere? So that's kind of what really got our attention and was sort of the motive, instigating idea behind this project. However, Solé and Montanou were network theorists. They mostly did this paper just because they were curious to see what would happen. They were not planetary scientists or atmospheric chemists or astronomers. So what we wanted to do is kind of like reproduce their work along a similar line, but in a much more sort of chemically rigorous fashion, towards looking at a bit more realistic portrayal of what atmospheric or planetary atmospheres look like. So to do this, we figured we needed a proof of concept, just to kind of test the idea of whether or not these network representations can actually tell us something useful about sort of planetary atmospheres that we couldn't get otherwise. And to test this, we actually started out with hot Jupiters. Now, since I'm an astrobiologist, you may be wondering, why did we pick hot Jupiters? As far as we know, there's no reason at all to believe that there is life on hot Jupiters, because pretty much everything is in a highly vaporized form. Well, for a couple of reasons. First off, they're one of the few exoplanets that we actually do have a decent set of data for their atmospheres because they're relatively easy to observe, as I'm sure many of you know. And secondly, their physical parameters are pretty easy to model. There are only a couple of major dominating ones, basically your heat, the temperature, the initial composition or metallicity, and the pressure level that you're looking at within the atmosphere. It's pretty much it, compared to, say, a terrestrial planet where there's a lot of different factors that go into sort of determining the nature and behavior of the atmospheric chemistry. So pretty much it was kind of like the simplest sort of planet that we could get. And the third reason, and this is something I found really interesting in the course of my research, is that we actually have a lot of sort of chemical kinetics data for this project, because it turns out that the conditions on a hot Jupiter are actually very similar to that you find inside an internal combustion engine in terms of temperatures and pressures and compositions, lots of hydrogen, lots of carbon, and a fair amount of oxidized species as well. And so there's a wealth of data from the car industry, from all their sort of experimentation and data analysis, trying to figure out better engines. So between all that, it seemed like hot Jupiters would be a good place to start. So sort of the first part of the pipeline that we developed for doing this analysis is that, people would take observations of the atmospheres of hot Jupiters and then build models of them, sort of the forward model, and try to figure out what the most likely atmospheric composition is for a given set of spectral observations. In our particular case, we used Vulkan, which is sort of an open source validated chemical kinetics model specifically for hot Jupiters. So we took that model data, extracted the reaction list, so all the reactions that are likely to occur based off of thermodynamics, as well as the reaction rates, and then we use that to build our network. And in our network, like I said, each species is represented by a point or node on the network, and then we weighted the edges or connections between them with the reaction rate to incorporate some of that kinetic data that I mentioned earlier. So one of the major things we were looking at was whether or not we were able to discern how far away the planet was from equilibrium. And the major reason we're doing this is because usually if a planet's atmosphere is away from equilibrium, that means something interesting is going on. And biology in particular has a real tendency to push its environment away from chemical equilibrium. And something that we're hoping to do further down the line is to be able to differentiate between disequilibrium that's driven by, say, biology versus disequilibrium that's driven by, say, photochemistry or some other process that isn't necessarily biological. So obviously, disequilibrium is something we're definitely very interested in. For the purposes of this research, though, we sort of quantified disequilibrium using vertical mixing coefficient, which, when you're talking about hot Jupiters anyways, refers to, as the name suggests, how much the vertical layers of the atmosphere are intermixed with each other. At a vertical mixing coefficient, or KZZ is the other term for it, of 0, we're assuming that there's no intermixing between the layers. Each layer is perfectly stratified, and each layer has also reached thermochemical equilibrium. Whereas if you have a KZZ that's above 0, you're assuming that there's mixing between the layers, and the greater the KZZ, the more mixing there is, the farther away you are from equilibrium, because, for example, you may be getting gases from sort of the deep, hot, high pressure parts of the atmosphere being dredged up into the cooler, lower pressure parts of the atmosphere, which would, say, supply those upper layers with species that thermodynamically would normally not be favored in terms of formation. And if your KZZ is high enough, you're getting that sort of material dredged up faster than sort of thermochemical equilibrium can sort of get rid of it. So like I said, basically the simple version of this is that the higher the KZZ is, the further you are away from equilibrium, at least for our purposes. So we built this network. We've weighted the edges based off of the reaction rates. We have a way to quantify equilibrium or disequilibrium, which is, like I said, again, something we're very much keen on looking at. Where do we go to from here? So, well, we take these networks, we measure their properties. Again, that would be stuff like degree and average source path length, the measurements that I mentioned earlier. And then from that, we take that as well as the initial conditions, the temperature, the metallicity, and the pressure level. And we use all that combined to build an interpolation function. And this allows us to essentially generate very large data sets without necessarily having to go and run 10,000 atmospheric models. Because basically what the interpolation function does, we can take then a set of random initial conditions of temperature, metallicity, and pressure, usually sampled in our case from a normal distribution, feed them in, and then the interpolation function will say, okay, based off of the data I've already been given, if we were to actually model planets with these initial conditions from this normal distribution, and then go and build networks from those models, the most likely network property of those networks would be this. So basically, it gives us a way to get really large sets of network measurements without actually having to go and build the models, which is really handy since running 10,000 models on Vulkan would take a very, very long time. So this is a bit of a shortcut. So like I said, it was a normal distribution that we were feeding into the interpolation function. When I talk about like the temperatures of the distributions, that refers to what the mean of the temperature distribution of initial conditions was. So for example, if I talk about low temperature distributions, that's going to be probably drawn from a normal distribution centered around 1200 Kelvin, whereas a high temperature distribution might be centered around 2000 Kelvin. Just to clarify that. So we built our interpolation function. We fed this 10,000, or the set of 10,000 normal distributions of initial conditions, and then gotten a whole series of distributions of network properties. What do you do with them? So one thing we did with them is we decided, okay, how well does this pipeline cope with uncertainty? Since obviously with the measurements that you take spectroscopically in real life, you're going to have a lot of uncertainty in those. Can we account for that, or will that just completely wreck what we're trying to do? So we would run trials where we would feed in property, or rather initial condition distributions where there was say a 50 Kelvin uncertainty in the temperature, or even up to 1000 Kelvin uncertainty in temperature, and see what happens. Another thing we did was to say remove an important reaction pathway, like the conversion of CH4 to CO as temperatures increase, because we may not have complete reaction lists for some of these planets, depending on how good our data is. Will that affect our results? And then lastly, if we feed in the network properties along with the actual conditions into a machine learning algorithm, how good are those machine learning algorithms going to be at predicting, or rather, are the network properties going to allow us to infer system properties better than other measurements we could potentially take of a planet, at least in terms of running it all through machine learning algorithms. So these are some of the initial results. This slide I mostly threw in because it's very pretty, but essentially what it's telling you is that the top row is going to be the abundances of a couple key compounds from left to right, CO, CH4, and NH3. The lighter the shade, the higher the abundance. And then the bottom row, going from left to right, is the mean degree, the average source path length, and the clustering coefficient. Clustering coefficient being sort of a measurement for kind of how clickish compounds are. If two compounds react with each other, do they also tend to participate in reactions that involve both compound or the same compounds as well? So basically, do they tend to stick together or not? And this didn't tell us a whole lot, but it did give us some interesting glimpses as to what might be going on here. First off, temperature is going to be on the x-axis, going from 400 Kelvin to 2200 Kelvin, and it looks like, yeah, changing the temperature is going to change both the abundances, as one would expect, but also the network measurements. So seeing that was a good sign, because it shows that our measurements are sensitive to actually changing physical conditions. And then going up the y-axis on the left is going to be the KZZ. So the further up you go, the farther away you are from equilibrium. And again, the network measurements do show sensitivity to that as well. So that's all very encouraging. The network measurements are actually at least responding to changes in physical conditions. If we didn't see this, we'd be very concerned. So this is when we get into the actual real results. So these are the network property distributions that I told you about that were generated by the interpolation function. In green, you have the equilibrium case. In purple, you have the case of KZZ is 10 to the 10. So that's very, very far away from equilibrium. And can you distinguish from the two distributions from each other? And it turns out, yeah, you can. With some better than other. The top measurement, delta G, is basically a thermodynamic measurement. It's not technically a network measurement. We threw that in just as a point of comparison. It's based off of the work that Josh Christensen-Totten has done with the measurement phi, if any of you are familiar with that paper. So that was just kind of a point of comparison. But looking below that, you have all the different network measurement distributions. And it turns out, yeah, they are pretty distinguishable from each other. So that was a good sign. And I should note that this set of distributions was from 1200 distribution. The initial distribution was centered on a value of 1200 Kelvin. So this is sort of a low temperature regime. Another thing we did in this particular case is what happens if we remove a critical pathway? Can we still distinguish between the two? And in this case, the solid line is the regular set of reactions. The dotted line is when we remove the CH4 to CO pathway, which, like I said, is really important in hot Jupiters. And it turns out, yes, at least with some of the measurements, like clustering coefficient and average source path length, you can definitely tell if the critical pathway is present or not. So that was also a very, very good sign. And then sort of lastly, this was the machine learning experiments I was talking about. And essentially on the y-axis is going to be the accuracy at predicting the KZZ value based off of whatever it is, whatever metric was set in. So on the left, you have that delta G value again, not very useful, relatively speaking, for predicting the KZZ value. And the spread refers to how much uncertainty there was. So 50 is uncertainty of 50 Kelvin in the initial temperature, going all the way up to 1000 Kelvin in the initial temperature. If you look at abundance, so that's just looking at abundances of CO or CH4 in parts per million, which again is sort of a more direct measurement. Better at predicting the KZZ, but its accuracy does tend to drop off, relatively speaking, as temperature increases. If you look at the topology, so that's going to be network topology, it's a lot more robust to a much higher temperature. So this was also really, really encouraging to see that essentially these approaches are going to hopefully give us a better degree of accuracy, at least of inferring things like how far away you are from equilibrium. So the next step from here, which is what we are currently working on, is going to be looking at terrestrial planets. In this particular case, we're using PyAtmos as our model, or just Atmos rather. And that work is underway as we speak. And hopefully we will have results about that by the end of the summer, fingers crossed. So anyways, just kind of to wrap things up. So network measurements can, in fact, tell us about atmospheric disequilibrium, and at least when it comes to integrating machine learning algorithms, can potentially do it better than other measurements, even when we're dealing with, relatively high levels of uncertainty in observations or weirdness like missing key reaction pathways. And we think the reason this is probably happening is because, like I said, we're able to incorporate the kinetics data, the reaction rate data, into the edges, which is in turn reflected by the topology. And that is essentially incorporating information, from, say, terrestrial lab experiments here on Earth that you would not normally have access to in other methods of sort of quantifying the atmospheric chemistry of exoplanets. So we think that's probably why we're getting higher accuracy. But yeah, it's really, really encouraging. Still shows a lot of signs as potential for a biosignature, but like I said, hopefully we will have a better sense of that by the end of the summer, because right now we're doing trials of comparing terrestrial planets that have abiotic atmospheres versus terrestrial planets that have biologically intermeshed atmospheres. And yeah, stay tuned. Are there any questions?
Thank you so much, Tessa. That was a great talk. So yes, there is a question in chat, and if anyone else has any questions, please feel free to raise your hand or put them in chat. I'll go ahead and read Rick Constantino's question in chat, who asked, have you or someone applied such analysis to other solar system atmospheres like Venus, Mars, Jupiter? And it might be interesting.
We are hoping to do that. Yeah, we are hoping to do that. That's also going to be part of it. Right now, we've just been working with like Earth-like terrestrial planets, just because we've got a model for that works really well. But we are hoping, to increase the diversity of planetary atmospheres that we're looking at. Because I'm really keen to see what happens when we feed in Venus or Titan or Mars. Whether or not that changes things. And which it probably will, at least I certainly hope so, but more importantly, how does it change things?
Right. Really cool. Does anyone else have any other questions? I guess one from me, Tessa, is you were talking about like how your model is going to handle uncertainties, and that you've done some tests and it's working well, but what sort of uncertainties do you feed into it right now? Like, do you look at any uncertainties in terms of the actual planet properties, like radius or anything like that?
Not sure as much in, let's see here. Not as much in terms of radius, but in terms of composition, yeah, metallicity, we had like 3 orders of magnitude of uncertainty that we looked at. Doesn't seem to affect it too badly, so that was encouraging to see. In terms of the pressure level, so how deep the atmosphere we're looking, and just how thick the atmosphere is. Mostly we didn't do as much with radius because Vulcan, at least the way I was taught to use it, wasn't as set up for that. Now that we're moving into terrestrial exoplanets, there's probably going to be a lot more sort of variety in terms of the composition and radius and gravity and possibly star type as well.
Gotcha. Does anyone else have any other questions for Tessa? All right. Well, if not, Tessa, thanks again for coming out and speaking with us today, and I hope you have a great rest of the week.
Oh, thank you.
All right. Take care, everyone. We'll talk in 2 weeks.